at the top, concurrent lines are defined as 3 or more lines that intersect at one point. Concurrent lines, 3 or more lines that intersect at one point. Unlike our transversals back in chapter 3, they had to intersect at least 2 points. Concurrent lines will all meet at the same point. The point of concurrency is where they intersect at then, is the point of intersection of concurrent lines. We're going to have different types of lines or concurrent lines and different types of point of concurrencies. And we're going to give them specific names, the points of concurrency, but that's just where all the lines would intersect at. We have 3 theorems today. They don't have any names to them. 5-6, the top one states that the perpendicular bisectors of the sides of a triangle are concurrent at a point that is equidistant from each vertex. Okay, so you don't have my little drawings. I'm going to go up here one at a time, but you can follow along. In this triangle, here's one perpendicular bisector of the side. Forms a right angle, cuts it in half. Here's a second perpendicular bisector. It's cutting the right side in half, making a right angle. Third perpendicular bisector. All 3 of these perpendicular bisectors meet at a point. Since they all meet at one point, we would call them concurrent lines, and this would be the point of concurrency. So it says the perpendicular bisectors of the sides of a triangle are concurrent at a point that is equidistant from each vertex. So this blue point is the same distance from vertex A as it is from vertex B as it is from vertex C. So those 3 blue lines that I drew in there are all congruent. What? Yeah, they would. I just had it in a different color, so I just picked 3. Yes. So the point of concurrency of the perpendicular bisectors is equidistant to each vertex or to each angle. And that's your theorem 5-6. I don't know if you want to draw a little sketch next to it or something. Perpendicular bisectors are concurrent at a point that's equidistant from each vertex. From 5-7 then, it says the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. So here's one angle bisector. I'm cutting angle, we'll call it angle A in half. Here's the second one. We'll say that's angle C. It's bisecting angle C. And then I could draw in a third angle bisector at B. All 3 angle bisectors are concurrent lines because they intersect at one point. This one point is equidistant to the sides. So the distance this point is, we'll call it X, from the side BC has to be the same as the side AB as it is from AC. So those 3 red lines are going to be congruent. The angle bisectors are concurrent at a point that is equidistant from each side. It may not be the same distance to each angle, but if I start here, 3 people start here and walk out to the edges, they should all walk the same distance. Okay. All right. Okay, so we're going to talk about circumscribed circles and inscribed circles. A circle is circumscribed about a polygon when the vertices of the polygon are on the circle. When the vertices of the polygon are on the circle. When a circle is circumscribed about, the circle's on the outside, and the polygon will be on the inside of the circle. And each vertex of the polygon has to sit on the circle. Over to the right there, you have a circumscribed circle because it's going about or around the triangle. Each vertex of the triangle, Q, S, and R, sit right on the circle. If you had something where it was like that, you wouldn't say the circle is circumscribed about that triangle because not each of the triangle's vertices hit the circle. So this would not be a circumscribed circle, although it goes around it. If I look at theorem 5-6, right above us, it says the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant to each vertex. So if I look at your circumscribed or your inscribed triangle here, here's a perpendicular bisector of SR, perpendicular bisector of SQ, perpendicular bisector of QR. Those three blue lines are concurrent at point C. And according to this theorem 5-6, it says that this point must be equidistant to each vertex. So the length of those red lines are all going to be the same. QC equals SC equals RC. Using theorem 5-6. Now look at the red lines in relation to the circle. They start in the middle of the circle and they go out to the edge. And they're all the same length. What do we call the segment in the circle that starts at the middle and goes to the edge? Starts with an R. The radius. So actually these are describing the radius of the circle. Radii of circle. C would be the center of the circle, or it's called the circumcenter of the triangle, which is the point of concurrency of the perpendicular bisectors. Circumcenter of your triangle is also the same as, I'm going to say equals, the center of your circle. They're the same point. The circumcenter of the triangle is the center of the circle. All right. We'll step back a little here and just look at a median. A median of a triangle is a segment that goes from the vertex to the midpoint of the opposite side. It's a segment that goes from the vertex to the midpoint of the opposite side. Has to start at a vertex. Otherwise, it's not a median. Since they have to start at vertices, how many medians can exist inside of a triangle? Larry? 3 of them. Triangles have 3 vertices, so you're going to have 3 medians. One of them is drawn for you. It goes from the top vertex, midpoint to the other side, since the left half is equal to the right half. Vertex to midpoint. The blue one there is a median. Vertex to midpoint. The red one is a median. The medians are going to be concurrent lines. The 3 medians of a triangle will always intersect in one point. This point of concurrency is called a centroid. And if you look at the very bottom blank on this side, it says the centroid of a triangle is point of concurrency of medians. Your centroid of a triangle is the point of concurrency of the medians. It's way at the bottom of your notes. There's a theorem that goes with centroids. That's theorem 5-8. It says the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Centroids cut the medians into a 1/3 and a 2/3 section. So GE, that's a median. The centroid there, C, is cutting it into a 1/3 and a 2/3 portion. FH, median. HC would be 1/3 of the length. CF would be 2/3 of it. JD is another median. CG is going to be 1/3 of that total length, and CD will be 2/3 of that. So if I say that the length of DJ is 21, what would be the length of CJ? 7, because it's a third of it. So 21 divided by 3 would give me 7. What about DC then? What would DC be? 14. 21 minus 7 gives you 14. If I said the length of DJ was 30, then CJ would be how long? 10. Because this is 1/3 of the whole line. If the whole line is 30, divide that by 3, this would be 10. Therefore, CD would have to be 20, because they have to give you a total of 30. If we said that HC was a length of 13, how long would HF be then? 39, good. This is 1/3 of the line. So to get the total line, you need to take it times 3 now. So 13 times 3 would tell us that HF is 39. Oh, let's do one more of these. If EC is 12, then how long would CG be? Is this the 1/3 or the 2/3? 2/3. So how many thirds make up 2/3? 2 of them, right? So then this would have to be 6, and this would have to be 6, so then CG is going to be 6. If they give you the 2/3 section, you divide that by 2 to get 1/3 of it, and then your whole length, GE, would have to be 18. Okay? Your pictures are going to be drawn to scale for us today, so the part that looks smaller will be the 1/3 section, and the part that looks bigger will be the 2/3. But according to the theorem, it always says the 2/3 section goes to the vertex. So your 2/3 will always go centroid to vertex, centroid to vertex, centroid to vertex, if it doesn't look right. But they do look right today, so you can go off looks, all right? Okay, one more little rule here, and then we can start applying these. So a circle is circumscribed about when the circle's on the outside of a polygon. If the circle's on the inside of a polygon, it's called an inscribed circle. So a circle is inscribed in a polygon if the sides of the polygon are tangent to the circle. The sides of the polygon are tangent to the circle. We'll hear the word tangent a couple times this year, well, more than a couple times, but it has a couple different meanings. Tangent here means that it intersects at one point only. So circle I, based off the center here, where the circle intersects BT is at point Y. It's only hitting it at that one point on that side. And the left side, the circle only hits it at point X. And at the bottom, it should only be hitting it at point Z, but my lines are so thick that it looks like they're intersecting at more than one point. Tangent means to intersect at one point. This is using theorem 5-7 at the top, the angle bisectors of a triangle. VI, TI, and UI are all angle bisectors. So they are concurrent at a point, I, that is equidistant to each side of the triangle. So IY, IX, and IZ are all the same length. That's using theorem 5-7. Now in relation to the circle, those lines start at the middle and go to the edge. So they're called what in relation to the circle? This is an R. Radius. These are all the radii. So point I is called the incenter of the triangle, which is also known as the center of the circle. Incenter of a triangle is the same as the center of the circle that can fit inside of it. I would say that this is an inscribed circle because it's on the inside of the triangle. You're going to use theorem 5.6 and 5.7 to find the centers of circles, depending on if the circle should be on the inside or the outside. Yes. Right there? Oh, I never did define that. The incenter of a triangle is the point of concurrency of the angle bisectors. This. The last vocab word on the top of the other side is the altitude. And by definition, the altitude of a triangle is the perpendicular segment from the vertex to the opposite side. Vertex is the the altitude is the perpendicular segment from the vertex to the opposite side. Perpendicular means they're going to make what? A right angle. Good. Since they're starting at a vertex, how many altitudes are going to exist in a triangle? 3 of them. Okay. Today you won't be responsible for drawing them, but tomorrow on tomorrow's worksheet, you're going to have to draw the altitudes and the medians for given triangles. So this top half or top third or whatever should help you for tomorrow. If you have an acute triangle, the 3 altitudes will all be inside of it. You have one of them already drawn in, the one from the top vertex. You could draw in one from the left vertex to make it perpendicular to the right side, and then draw one in from the right vertex so that it's perpendicular to the left side. When you have all 3 of them drawn in, they're all on the inside of the triangle. Altitudes of acute triangles all exist inside. Later on, we'll think of the word altitude as height. The altitude is representing the height of the triangle. If you think back to like when you found areas of triangles and stuff, or if you think about an airplane, its altitude tells us how high it is in the air. You can also refer to it as height. A right triangle. On your notes, you already have 2 of the altitudes drawn. From the top vertex to the opposite side so that it makes a right angle is the right side of the triangle. So that's 1 altitude there on the right side. The bottom left vertex, if I want to draw the perpendicular segment to the opposite side, well, that's just the bottom of the triangle. So the bottom of the triangle and the right side of the triangle are 2 of the altitudes. Then your third one, when you draw it from the right angle, goes right through it. So in a right triangle, 2 of the altitudes are the sides, or they're called the legs of the right triangle. And then 1 of them is on the inside. And that's true for every right triangle. The 2 sides that are perpendicular to each other are 2 of the altitudes. And then the obtuse triangles, these are the most difficult ones to draw, and we'll practice tomorrow to draw them. The 3 altitudes, 1 of them is on the inside and 2 will be on the outside. So if you want to try and mimic what you have up there, we'll practice tomorrow, so it might help a little. But you just have to remember altitudes go from the vertex and then they make a right angle with the opposite side. Altitudes have to be perpendicular. I remind myself, if I want to know how tall I am, I wouldn't stand at a slant to measure that. I would stand perpendicular to the floor. Height, altitude has to be perpendicular. Medians go to midpoints of the other side. Median, midpoint. Alrighty. Here we go. Let's try this first one. You have one of these on your worksheet today. Find the center of the circle that circumscribes triangle X, Y, Z. Flip it over to the front side for me. We have two pictures where the circle is on the outside and one's on the inside. Do we want to find the in center, or do we want to find the circumcenter? Look at the two pictures from the front side. Which one would match mostly with ours? Ethan? Yeah, we need to find the circumcenter. That's the top one. That's the one that has the circle on the outside. Okay, flip it back over for me and look up the definition. Circumcenter is the point of concurrency of what? Good, perpendicular bisectors. So we don't need in-center. Since the circle's circumscribed about, we're trying to find the circumcenter. See how those base words are the same? Maybe those are the prefixes. I don't really know. So what we have to do is find the perpendicular bisectors of each side. Perpendicular means what? Right angle. Bisect means two. Okay, so the bottom side of the triangle is a horizontal line. I need to draw a line that's perpendicular to it, so it's going to be what kind? Like if my line's horizontal and I want a perpendicular line, it should be vertical. And it has to bisect this side, or cut it in half. Well, it goes from 1 to 5. So what's halfway between 1 and 5? 3. So draw a vertical line through 3. That blue line is the perpendicular bisector of the bottom side. I gotta find them all. So I gotta find where they intersect at, because that gives me the circumcenter. So the left side of the triangle is vertical. Therefore, perpendicular to vertical will be horizontal, and it's supposed to bisect it. Well, the vertical line here, this left side, goes from 1 to 7. So what's halfway between 1 and 7? 4. So draw a horizontal line through 4 there. That red one is the perpendicular bisector of the left side. Where 2 of them intersect, is that where the third one's going to intersect, if they're all supposed to intersect at the same point? So is there a need to find the third perpendicular bisector if I already know where these two are? Good. Where those two lines intersect, that's the circumcenter, which is the center of the circle. What is its ordered pair? Where do they intersect at? What's the x value? What's the y value? So then the center of the circle is at 3, 4. Circumscribed circles, you have to find the circumcenter. That's like the one, Larry, that I did up there on that board when you asked that one at the way beginning. Find the perpendicular bisectors.
But will they not always intersect inside the circle?
Nope, they won't always intersect inside the circle. Good question. What kind of triangle would you call this one? A right triangle? They'll always intersect on your hypotenuse. This is called your hypotenuse. An acute triangle, they'll intersect inside of the circle. And an obtuse triangle, they'll intersect outside of the circle. They'll intersect like way out over here. But it'll still be the center of the circle when you have it drawn out. Cool, huh? All right. Number 2. City planners want to locate a fountain that is equidistant from 3 straight roads that enclose a park. Explain how they can do this. So I have 3 roads here, Andover, Mariposa, and Highway 101 that create a park. What's the shape of my park? The triangle. Okay. I want to put a fountain inside of the triangle in the park so that it's equidistant from each side of the park or each road. Flip your paper over and read through Theorem 5.6 and 5.7. Find the one that talks about a point being equidistant to the sides. 5 point what? 5.7. Okay, so Theorem 5.7 says such and such and such and such are equidistant from the sides. What are all the stuff at the beginning? The what are equidistants? What kind of bisectors? The bisectors of the angles. Good. So the city planners need to find the point of concurrency of all the angle bisectors. Where the three angle bisectors intersect, that's where they want to put their fountain at. It's a volcano fountain since I used red. Okay. So explain how they can find the location. Planners need to find point of concurrency or intersection of the angle bisectors. So on 3, it says that M is the centroid of triangle WOR. Centroid, that's where the medians intersect. And what fractions does it cut it into, the medians? 2/3 and 1/3 then, obviously. Yes, good. So on 3, it tells us that WM, that's this part, is a length of 16, and we have to find MX and WX. You can go based off of looks today. Would WM be my 2/3 chunk or my 1/3? 2/3, because it's bigger. So if 2/3 is 16, what's 1/3? 8. Just cut that in half. So that would mean that MX is 8. 1/3 of it is 8. And my whole line, WX, would have to be how long then? 24. You can go off looks there. Medians intersect at a centroid. We have a handful like this today where they ask you what type of segment it is. So they want to know if segment KX is a median and altitude neither or both. Remember, medians go to midpoints. Altitudes are going to be perpendicular. Like if you want to measure your height, you wouldn't stand crooked. You would stand perpendicular to the floor. So when I highlight segment KX, would you consider it a median? Does it go to a midpoint? You should nod your head yes. Isn't X cutting LM in half on the bottom? Yeah, because LX is congruent to XM, so we consider it a median because X is a midpoint. Would you consider it an altitude? Yeah, because it makes this right angle with that other side. So if it's a median and an altitude, then our final answer would be both. What would you call segment MY in this picture? MY? A median, good, because Y is a midpoint. Can't be an altitude, there's no right angle, so MY would be a median, good. Okay, number 5, this is like number 1. Find the center of the circle that you can circumscribe about the triangle. So that means the circle is going to go on the outside, and it has to hit the 3 vertices there. So you have to find the center of that blue circle. Just like we did number 1. Did we find angle bisectors on number 1? Bless you. Or perpendicular bisectors? We'll look back at number 1. What did we look for? Angle bisectors or perpendicular? Did you measure any angles today and cut them in half? No, so what did we find then, Sarah? The perpendicular bisectors, yes. You have to find the perpendicular bisectors of each side. Where they intersect is the center of the circle. So on the bottom, -8 to 0, if I want to cut that in half, where do I have to go through? -4, and since it's horizontal, the perpendicular line would be vertical to that. On the right side, it goes from 0 to 6, so if I want to bisect that, where do I pass through? 3, and perpendicular to a vertical line is horizontal. Where 2 of them intersect is where the third one will, so you don't have to find the third one. That point of intersection is the center of my circle. What is that ordered pair for that point of intersection? -4, 3. This would be the center of your circle. So you're circumcentered of the triangle too. Okay. 2 examples. You've got one of those on your worksheet today. We already did number 6 when I asked you on number 4. We said that MY is a median because it's going to a midpoint. Y is a midpoint. It cuts that left side in half. Let's just do number 8 so I get one of these with you guys. It says that, or we have to figure out which ones are medians and altitudes. VZ would be your altitude. It's perpendicular. SY and PX are both medians because they're at midpoints. So M is my centroid, where the medians intersect. If the length of SY is 15, what would be the length of MY? 5. This is the 1/3, 2/3. Centroids cut it into 1/3 and 2/3. So MY would have to be 5. They gave me the total length divided by 3. SM, the 2/3 chunk, would be how long then? 10. Because 10 plus 5 would give me that 15. Okay, hopefully that's enough to get you going on your worksheet.